So sorry for not knowing a single word in Turkish, so you have to forgive me, because I'm a Brazilian Japanese, so it's hard enough to be talking in English today. And my name is Edson Yanaga. I'm a director of developer experience at Red Hat. My Twitter handle is @Yanaga, just in case you want to follow me. I talk a lot about DevOps, microservices, Java, and any stuff related between that. And today I'm going to talk about migrating to microservices databases, because the #1 question that I always receive when discussing microservices with people, okay, we get the code part, we had some remote communication and everything else, but how do I deal with my data? So I didn't have an answer for that, but in the past 3 years I've been doing a lot of research, talking to a lot of different teams and developers worldwide, and I was able to collect some of these answers on this talk. I'm also a Java champion and a Microsoft MVP, and I work for Red Hat, which I believe is a very cool combination. And as far as Google can tell me, it's a unique combination so far. And if you want to know more about this subject, I released last year this book from O'Reilly, Migrating to Microservice Databases. So everything I'm going to talk today, you have like in deeper detail on this book. If you don't want to type this full URL, you can go to my Twitter profile. The pinned tweet has a link to the ebook. You can get it for free because Red Hat developers bought the royalties of the electronic version. So you can just click and download. And we're going to start the discussion about talking about zero downtime, because I believe that most of you are already aware of we need to have continuous deployment pipelines, we need to manage state, we need to be able to quickly release our versions into production. But if we truly want to get into this DevOps bandwagon, we must be able to deploy like to have zero downtime deployments. And the basic premise of having a zero downtime deployment is that we need at least a kind of blue-green deployment, which means that we'll have 2 equal environments running into production, so I can update one environment with the new version while the old one keeps running. So if anything goes wrong, I can roll back my version to my previous environment, and nobody gets broken into production. I have 2 different versions. And if you think about this kind of architecture, it's not that hard to implement. We've been doing this for the past 15 years. First manually, but these days we can do that automatically with the deployment platforms that we have today. But if you think about that, I like to say that with code, it's kind of easy to achieve this kind of architecture, right? You just deploy 2 different versions of your applications into production. But with states, it's much harder. It's very hard for you to manage state when you have 2 different versions running of your application running into production. And when I talk about state, you can have 2 different kinds of state. You can have ephemeral state, which is usually the kind of state that you have. I think it's falling. Sorry. You can have ephemeral state, which is usually the state that you have in your HTTP session, which for some sorts of application you can afford to lose it. But of course, if the user is typing a 200 field form and you decide that, well, you lose your ephemeral state and he or she needs to start over again, you have a very unhappy user. But worst case, for most of the applications, the user will have to log back in again. But when we're talking about persistent state, which is usually the state that you store in a relational database, you're not allowed to afford any data. You can't have any inconsistencies in your data when you have multiple versions of your application running into production. So the question is, how do I deal with my relational database if I want to perform blue-green deployments and if I want to perform zero downtime deployments of my applications into production? So the answer goes through multiple steps, and the first step is that first, you need to automate everything. You're not allowed to perform manual schema migrations anymore. You're not allowed to email your SQL statements to your DBA overnight. You're not allowed to attach that to a Jira issue. You have to do that automatically in your deployment pipeline. And 2 of the most popular tools, I thought that only the Java worked, but I just realized that teams that work with multiple different platforms are using these tools too, except for the Rails community, because Ruby on Rails has their own built-in migrations. But apart from them, most of the teams are using these 2 tools, Flyway and Liquibase, which just happen to be implemented in Java, but they work, of course, with any language, any platform. Both of them are feature complete. I don't have a strong preference for one or the other. I've just been using Liquibase in my past 5 or 6 projects. That's why that's my current choice. But Liquibase has a much older code base. So some more mature teams have been using Liquibase for the past 5 years, 6 years, something. So they keep using that. But I don't have a preference. They both automate your schema migration. They both support metadata-based migrations. They both support SQL statements for migrations too. So it's up to you to decide which one do you prefer. You cannot, if you're using Java in your project, you can attach these tools to the startup phase of your application, which used to be a best practice, but now that we're talking about containers and multiple instances of my applications running into production, you don't want your application checking if it should perform a schema migration for the 10 instances that are starting up right now. So my particular recommendation for this is that you should attach the schema migration to your deployment pipeline. You do that in one step before you update your code in your production database using one of these tools, okay? So for at least my opinion, you should be using these tools as part of your deployment pipeline and not as part as the startup of your application. But how do I achieve zero downtime migrations? Because sometimes you need to perform an alter table, you need to update the data of some columns. You must be able to do that with zero downtime. So the answer for us to achieve zero downtime migrations is that first, your migrations need to be back and forward compatible. Any kind of migration that you apply in your database must be compatible with the next version, and the next version must be compatible with the previous one. It might look hard in the beginning, but many teams are using this technique worldwide. And to be able to have back and forward compatible migrations, you have to break your current migrations into baby steps, which means that for most of the use case, you have the smallest possible batch size. So if you used to issue 100 statements, SQL statements, schema migration to your DBA, maybe you have to break that into multiple, like maybe 100 different migrations. Also, it means that if you used to have like too many locks when applying your schema migrations, like for example, if you need to update a column in your database and that update leads to a lock, well, you have a 2B row table and you update the column and you have a 5-minute lock. Well, 5-minute lock means 5-minute downtime of your application to production. You're not allowed to do that anymore. Maybe you have to break your update statement into multiple smaller statements, so each one of them has like 5 milliseconds downtime, which can be affordable for most of the use cases. So that's some of the strategies that we'll need to apply. Sharding is the database term for splitting your update statements into multiple smaller ones. So you need to shard your update statements. And just to give you a small examples, if you used to do alter table customer rename something to the other thing, maybe now you have to issue first an add column statement that shard multiple updates to your database table, and then later delete the column. That's just an example. That's not how it works. But as I said before, I've collected many different scenarios from many teams worldwide, and these are the 4 basic zero downtime migrations that you can apply to your database. If you check that, you see that I'm only talking about columns, but if you think about a table as a set of columns, if you want to modify a whole table, you just need to apply these steps like multiple times, one after the other. You're able to perform your schema migration successfully when using tables too. So I'll try to dig through them very quickly because, but if you want to look at that in a deeper format, of course you can read the book. Chapter 3 of my book has these migrations in a detailed format. So because of the time, I won't be able to discuss much about that later because I have a lot of content. And the first scenario is add a column. If you look at these numbers, 1, 2, 3, and 4, each one of them is a different migration, which will be deployed in a different version of your application into production. So if you want to add a column in your application, first step, you do alter table add column. Second step, your code computes the read value and writes to the new column. When I say compute, if you can compute the new value from current state in your database, you do that. If you're not, maybe you create a default value and update to the table. It really depends on your use case. And third step, you update the data using shards from the old columns, from the old rows in your table. And fourth step, your code reads and writes from the new column. If you did that in at least 4 different steps, you were able to achieve zero downtime migrations, because each one of these versions is back and forward compatible. The previous version is compatible with the new one, and the new one is compatible with the previous version. And I can't emphasize this enough. Between each one of these versions, you are going to open your SQL CLI, you're going to issue multiple select statements to check if your application is reading and writing the right information on your database, okay? You need to do manual checks to check that everything is going correctly. And this is the simplest possible migration that you can do at a column. Next one, rename a column. This is the most complicated one. If you want to rename a column in your database, you need at least 6 different versions. First step, alter table add column. Second step, your code reads from the old column and writes to both. Third step, you copy the data using small shards from one column to the other. Fourth step, your code reads from the new column and writes to both. Fifth step, your code reads and writes from the new column. And sixth step, much later, you just mark the column for deletion. You never delete the column immediately after. And why that? For you to be able to achieve zero downtime migrations, you're never allowed to perform a destructive statement in your production database, right? Deleting columns is a destructive statement, so just mark for that, so the DBA later in the maintenance window, he or she will be able to, well, nobody's using this column in the past 6 months, maybe it's safe for me to perform a backup and delete the column, okay? So this is the hardest one. And I know if you never did that, you might have doubts, does it really work into production? And many people have doubts about that. I'm always challenging people, if you find a bug in these steps, please report to me. But so far, in 2 years that I've published this, all the people that have tried these migrations, the ones that reported to me later, they said that it's working successfully into production. And even if you go to YouTube, I have a small video of a demo application that I showed how can you perform these multiple steps and showing the different versions of the application running without losing any state, and they work successfully managing the data. Okay. And next scenario, change type and format of a column. And if you see a pattern here, these are the exactly same steps for both scenarios, right? So, and it's a good thing, because if you rehearse the steps from one migration, you'll be able to perform the other one very successfully, because renaming and change the type and format of a column doesn't change much if you're not destroying anything in your database, right? And the last scenario is delete a column, which is basically don't. You never delete a column into production, because when you delete, you lose states of your application. And if you need to roll back your version, you don't have the data anymore. So you never delete your columns into production. You just stop using the read value, but you keep writing to the database, to the old column, because if you need to roll back, you still need the value from the old column. Then if you decide, well, nobody's using that data anymore, maybe in another version I can decide to stop writing and mark that column for deletion. So much later, 1 month, 2 months, 6 months, 1 year, doesn't matter. You just mark the column, and the DBA, he or she, will be able to access when will be the most convenient time to physically delete the column. So if you did that, you were able to achieve successfully zero downtime migrations. And I know it seems hard for most of us enterprise developers to be thinking about this. When I started this research, most of the teams that were using this into production were from startups. They have very mature software deployment pipelines. They're already deploying multiple versions per day. So if you deploy like 10 versions per day, it's very easy for you to deploy one of each of the steps in every single version. But if you're deploying one version of your application every 2 months, it will be very hard for you to perform this kind of zero downtime migrations, right? It would take you like at least 1 year to be able to roll a schema migration. So for you to be able to do that, first you have to solve another problem, which is that you need to reduce your batch size. You need to be able to perform like very fast release of your application into production, and you need a very mature software deployment pipeline. But after I've written the book, many enterprise teams were able to report back to me, maybe not in the old monolith, but in the new microservices that they're creating, they were able to accomplish the zero downtime migrations, because they have like very mature software deployment pipelines, at least on these new artifacts. So if they're deploying once per day, they are already able to deploy these zero downtime migrations. And for them, and after you get used to these migrations, you do that not only because they are zero downtime, but because it's also the safest way for you to deploy anything into production, because you never lose data. If you want to roll back, the previous version is running. You don't need a complicated rollback strategy for the data, roll back a backup or something like that, which is very hard to be able to do that successfully. So you just don't lose data, keep everything there, move this with which is the safest possible strategy, right? Next question is, well, how do I deal with my referential integrity constraints when I'm changing these columns? And sometimes you need to break some walls to make room for improvement. So the answer is that you need to drop all of these constraints and recreate when everything is done. This applies also to not-null constraints. When you're creating a new column and moving the data, maybe you need to remove the not-null constraints from both the old and new column and just apply the not-null constraints later when the migration is done. Okay? So this is the quick and not so easy answer, but that's how you need to apply these migrations. Okay? And that was about the zero downtime migration part. You might be wondering, why am I discussing zero downtime migrations in a microservice talk? Because in the past, the downtime of your monolith was equal to the downtime of your system. But now that you have multiple artifacts into production, you're not allowed to have, well, my system is not running because that small microservice is getting its database updated, right? So you have multiple teams, multiple databases, and every time people decide to update their artifacts multiple times per day. So maybe if you used to have like 99% availability in your system, now you have multiple parts. If you just start to multiply the unavailability of each one of your microservices, you'll have a very low number of your system. So you're not allowed to have that anymore. And that's why you have to solve the zero downtime problem into each one of your microservices, right? And digging into the microservices characteristics part of this talk, Martin Fowler did a very nice job trying to collect many of these microservice characteristics into his Blicky. But today we're only going to discuss this one, the centralized data management principle, which states that each microservice must own its own database, right? When we're talking about microservices, you have different people have different answers for that. I like to focus on the people problem. I think that when we're talking about microservices, we have a team, a very large team, and we have coupled queues, working queues. I can't release my piece of code because the other team didn't finish their part. So when they finish their part, now I can't release my part because I'm in the middle of something. So you have like coupled queues, and you need to synchronize the queues to be able to release an artifact. It's a very hard job. And when you have microservices, you're trying to uncouple the queues. So I can release my artifact whenever I want, so the other team can release their artifact whenever they're ready. But if you have a central database, you still have a coupled queue, because I can't release my artifact because I need to change the schema, and the other guys are still using the old schema. So you need to synchronize everybody. So if you have microservices, but if you're using a centralized database, you're doing it probably wrong, because you still have a coupled queue. Right? You're solving just part of the problem, but the synchronized release problem still exists in your team. So each microservice must own its own database. So the hard part is that most of us need to deal with legacy systems. Instead, that's the preferred approach for creating a microservice architecture. You always start with a monolith, and when your knowledge is mature enough about the domain problem, you just decide to break this monolith into smaller parts. But how do I get and extract this microservice part from my monolith, my old entangled monolith relational database, until I can achieve one database per microservice? I don't have an easy answer for that from the domain problem part, because it really depends on your use case. The answer usually goes through domain-driven design, bounded context, but you need to carefully analyze which pieces of your data changes together and which pieces of data changes apart. So that would be like good candidates for you to choose which piece of information to extract from your monolith. And I've did that before, but it takes like many weeks, months for you to be able to achieve that separation. And to be very honest with you, most of the teams, they do it wrong. when they try to extract it. On the first time they do that, they do it wrong. That's why it's so hard for you to extract your microservice part from your database. But after you decide which piece of information do you need to extract, I can help you on how can you integrate and distribute your data later, right? And that's what I'm going to talk right now. So I still have an old legacy monolithic database, and both my microservice and my monolith, they still need to integrate their data. They still need to read and write the same data from different pieces, maybe from the same database. How do I do that? So splitting is not easy. But integrating is not easy too. It's a hard problem. You need to integrate your data with multiple endpoints. You need to deal with consistency. So before I dig into the solutions, I have to give you a very quick and simple explanation of some consistency models. There are many. So if you study distributed systems, I'm going to oversimplify many of the concepts. I'm only going to discuss 2 different models, which is strong consistency and eventual consistency, right? How does it work? Strong consistency is the consistency model that you think that you have in databases. On relational database, it means that if you have 5 different nodes of your application, and you decided that you want to update the data on this node, so you have a variable i equals to 3, and you want to update the data on this node. Now I equals to 5. All of the nodes of the system, they must agree, like the information needs to be propagated to all nodes on the system before anybody can read the 5, right? I update here, everybody agrees, well, now I equals to 5, okay. Transaction is finished. Any new clients, now that when they issue a read, they will read 5, right? Before that, before everybody agrees, everybody reads 3. After everybody agrees, everybody reads 5. This is a strong consistency model. This is usually the model that you expect to achieve using distributed transactions. Second model, eventual consistency. You have multiple nodes in your system. You can update information in any node, but you can write here, you can write here, you can write here. When you have concurrent readings, you can expect them to have conflicts. When you have conflicts, you need a conflict resolution algorithm, and that's not the typical use case for enterprise information systems. That's why we usually don't use pure eventual consistency models. So the one that is useful for most enterprise systems is the strong eventual consistency model. How does it work? If I have 5 nodes in my system, I choose one of the nodes to be the canonical source of information, which means that writes are only allowed on this node. So when I say now I equals to 5 on everybody, and decide now I'll update my variable to 7. Now I equals to 7, but you have multiple different nodes. Any client connected to the other nodes will still be reading 5. Any client connected to this node will already read 7. And this data gets propagated to the other nodes with different latency requirements. So, well, I propagate the data to this node, then anybody connected to this node will get a 7 already, but other nodes will still read a 5, and these new ones will get a 7. Later, I decide to update the data here using a 9. So people can read a 9, people can read a 7, and the other one will still be reading a 5, right? So this is a strong eventual consistency model, which means that you will have different values in your system, but they are all correct, but some of them might be outdated, right? This is a strong eventual consistency model. And if you think that, well, I work for enterprise systems, I'm not allowed to have this kind of strong eventual consistency models, well, sorry, your banking application uses a strong eventual consistency model, right? Sometimes you go to your ATM, you try to withdraw some money, and you get the money, but the system, the internet, the connection, network connection is offline. The data doesn't get propagated to your mobile application. So when you check how much money you have in your mobile application, you still have the money, but don't worry, the bank never loses money. As soon as the transactions get propagated, you will have your money withdrawn from your account. That's a strong eventual consistency model, and that's the favorite approach for when using microservices architecture, right? You need to embrace the strong eventual consistency models. The other discussion is CRUD and CQRS. In fact, I have even another talk discussing these concepts in further depth. And I'll have to explain very quickly. traditional model for creating applications is CRUD. You have CRUD, create, read, update, and delete models. You use exactly the same models for read and write operations, both in your code and your database. Example, if you have a customer microservice and you're using a CRUD architecture, you have a customer class, you populate that customer class, you write to the database, you create queries using the customer class too, you retrieve customers and show that to your user. Right? So CRUD, most common architecture. In fact, I suggest very strongly for people to use CRUDs. Like 90% of the use cases are better served with CRUD architectures. And this architecture is so simple that you have like many scaffolding tools these days that can generate most of your code when using a CRUD. But depending on your requirements, you might want to embrace a CQRS architecture, which stands for Command Query Responsibility Segregation. You can have many different approaches for doing that, but I'll try to explain very briefly again because of the time. In the beginning, you have like customer microservice. You populate the customer object and you write that to the database. But then customer is a very big object, has many information, and your manager decides to add a requirement to the system. I need a customer report. When you create a customer report, customer is very big, but you need, for your report, you only need the ID, name, and email of your customer. So you don't want to query the entire database to memory just to create a report with these 3 fields. What do? You create a DTO class. You create a customer DTO class with just these 3 fields. You create a custom query, you populate this DTO, and you create the report, right? Congratulations, you just created a CQRS architecture. You're using different models for reading and writing. You write using the customer class, but you're reading the values using the customer DTO class. That's the simplest possible CQRS architecture. In fact, this is an oversimplification, because if you want to do that properly, you would have separate service interfaces, one for reading, one for writing, but that's a discussion for another day. And when you realize that, then you have another requirement. You have another report. Well, now you need the ID, the name, and the phone number, which is different from the email. What do you do? You create customer DTO2. Which is a very bad naming strategy, but you get the point, right? You created another CQRS representation of your customer data. But after you did that with multiple classes, you realize, well, if I'm doing that, if I'm doing CQRS in the codes, I'm not constrained to the code. I could be reading and writing from different points of information in my database. If you ever created a view or a materialized view because you needed to perform some complex aggregation of your data to generate a report, congratulations. You created a CQRS architecture with separate read and write models. You're writing to the customer table, but you're reading information from the customer view or customer materialized view. That's a CQRS architecture. And this architecture, this particular architecture, CQRS with separate read and write data stores, is the preferred approach for dealing with microservices databases. Because you have a microservice, it will be the right data store, and when you need to consume the information, you will have multiple CQRS read data stores distributed in your system. Last concept, event sourcing. Right? What is event sourcing? Event sourcing is basically a strategy where the state of your data is not represented by a snapshot information, like it's represented by a stream of events. Classical example of event sourcing is that the money that you have in your bank account. Nobody stores the money that you have in your bank account as a number in a row, in a column in your database. What do? You create a transaction table, and you just add debit and credit transactions to that. If all of the bank accounts start with 0, if you get all of the debit and credit transactions and apply them successfully, you have the current amount of money that you have in your bank account, right? So, but you might be wondering, well, if I have too many customers and I have too much transactions, it will become very slow for me to compute how much money do I have in my bank account, right? So what do you do then? You just create a CQRS read data store. So the true source of information is the transaction log. If I want to know how much money do I have there, I go to the transaction log. But if I want to have a fast read, I have a cached information on another column, another table, another row, which is just for performance reasons, right? So I write here, and this cached model can be updated synchronously. if I have a transaction in my database, or it can be updated asynchronously if I'm using some messaging system, right? So that's why event sourcing and CQRS are usually coupled together, because event sourcing is a very nice architecture. You have very fast writes. You have a free time machine. If you want to know how much money did you have like 2 years ago at 2 p.m. and 12 minutes and 13 seconds, you know, you can calculate that. If you have a free auditing mechanism, that's what all of the banks do. The banks, they have the cached amount. So what they do, they know how much money you have in the previous night. If you want to check everything, you apply the transactions from today, tonight, and when you check how much money I had yesterday, you apply the transactions, you compute, well, I should have this amount of money, how much money I have in the cached copy. Oh, they don't match. If they don't match, you raise a flag, you send that for manual auditing. That's what usually most of the banks do. But event sourcing, as you've seen, you have very fast writes and very slow reading. That's why you usually couple CQRS with CQRS for performance reasons. So the initial motivation for creating CQRS architectures were performance. And now that we're discussing when we're talking about distributed data, we're using CQRS mainly for integration. And that's the solution part. What I'm going to show you right now, again, very quickly because of the time, but you can read the book later. These are the scenarios that teams worldwide are using to be creating these CQRS read data stores. And the story behind that is, why do they need the CQRS read data store? Is that I've seen many teams failing with that. I want to create a microservice architecture. Okay, let's suppose I have a monolith. I've decided that customer is the ideal candidate for my microservice. I extract the data from my customer. I create a customer microservice. Customer microservice is the canonical source of information. All the writes go here. The reads can be done anywhere. Because I did a very nice architecture, I have a DAO, so I decide, well, the only thing I need to change in my architecture is that instead of writing directly to a database, now I'll change my customer DAO to issue some HTTP queries to my REST endpoint, and everything will work fine, right? You deploy that into production, you fail. Why is that? Because it's so slow, right? Reading and writing from a remote endpoint is very, very slow. Your system goes down because you can't afford this kind of round trips between microservices. And you think, well, if the system is slow, that's a performance problem. What you do, you add a cache. You add an internal cache. Now you have more problems. But I added an internal cache, and I added a hash map here, and things are faster, but not fast enough. I need more cache. You create an external cache service. You deploy a Redis service, and you have an external cache. Now, it's fast enough. But then you realize, well, but now in my monolith, I still have that 100 different reports that they were queuing with SQL, and they were joining the customer table directly on the database. Now I need to fetch the information from the database. Now I need to fetch the customer objects from the cache and join them in memory. And they realize that they have a huge maintenance problem because they have to change everywhere in the monolith. And the final solution, they realize, well, why don't we create a copy table here? So everybody writes there, but then the changes get propagated through some sort of way here. But then we created a copy table, which is a CQRS read data store, and we don't have to change any of the reports that we already have running. That's the final solutions that many teams agree, and that's the path that I suggest you to skip. You skip this REST endpoint, synchronous communication, cache, and everything, and you just go directly to the final solution, which is creating a CQRS read data store. I'm not saying that REST endpoints doesn't work. I'm just saying that you have a high traffic, a high read and write volume. A REST is not the perfect architecture for that. Maybe you could even do that use a REST endpoint for writes if you don't need high scalability on the write side. But usually enterprise information systems, they have strong query requirements. And for these use cases, REST endpoints are not good enough. You need to use CQRS read data store. So I'll go very quickly through these 9 different scenarios. Most of them you are already used. Shared tables, database view, materialized view, triggers, transactional codes, ETL, data virtualization, event sourcing, and change data capture, right? First one, shared tables. Both monolith and microservice read and write from the same database, which is the fastest data integration. You have strong consistency because you're using database transactions. It has very low cohesion and high coupling, which for most of the teams, it means just a hack. You're only allowed to do that if you know that you're going to change this immediately after, because that's the perfect excuse for not changing anything at all later, which means that, oh, I need to change the table here, but I can't change because the monolith is still using that. The monolith team, I can't change my tables because the microservice is using the same tables. That everybody is stuck forever on the same thing. So I consider this a hack, but if you're doing that very quickly, just for this version, and tomorrow I'm going to change, or next week I'm going to change for a more robust strategy, you can do that, right? Second approach, database view. You have the microservice here, you create a view in your monolith, and the monolith consumes from the view. This is the easiest one to implement because all databases as of this year, they support database view. You might have some performance issues because of the view. You always have strong consistency because of the transactions. One database must be reachable by the other, which means that if you have remote databases, you need, at least on Oracle, you need a DB link for that, and some DBAs curse me for that. But I've seen people using that, and it works. I did that myself in the past, and it works for creating this architecture. If you don't have strong latency requirements. Next improvement, if the view is too slow for you, maybe you can create a materialized view, has better performance, it can have stronger eventual consistency. If you update that on commit, it's a strong consistency. If you update that based on a trigger or interval trigger, it's eventual consistency. One database must be reachable by the other. And again, I implemented the solution myself for CQRS read data models, and it works depending on your latency requirements. I once integrated these. I had a service on Amazon. The other one was in their data center. I was able to create a remote DB link and update a remote database materialized view, just because I only needed to update my database every 30 minutes. And it took approximately 20 minutes for me to refresh the materialized view. So for this use case, it worked beautifully, and it took me like 15 minutes to be able to set up that. The other approach, database trigger. I have a trigger. Every time I commit something to here, I want to update my CQRS read data store. Depends on your database. You always have strong consistency because it's on commit, it's on the same transaction. But this also should be considered a hack. It only works for point-to-point integration. I only have one microservice and one CQRS read data store. And why is that? Because every time you change your data model here, you have to change all of the remote endpoints here. And if you have one write endpoint and 5 different read endpoints, every time you change here, you have to change the 5 remote endpoint. Every time you have to change the remote endpoint, you have to change here too. So it becomes a cascading problem. So I don't recommend, because I think that it has a very tight coupling. But some teams are working, and if you only have one integration to perform, that's a solution. Other solution, transactional code. It's the same use case as triggers. You just use another type of code to be able to perform that. You can use store procedures or distributed transactions. You have strong consistency because you're doing everything on the same transaction. You have possible cohesion and coupling issues. As I said, it only works for point-to-point integration. If you have one-to-many integration to be able to perform, this doesn't behave very well. ETL tools is the kind of tools that when you have like Pentaho, ClickView, or the other types of ETL tools. The ETL tools is already extracting data from your database, and you want to create and populate another remote database using these ETL tools. It's useful if your team already has an ETL expert. He or she is already performing a lot of integrations in your database, and you just need one more. So you just ask he or she to create this new ETL extraction and create this CQRS read data store. But if you have more than one, or if one of the teams doesn't have an ETL expertise, maybe you shouldn't be using ETL. But I've seen some teams using that because I already have an ETL expert. I just ask he or she. Takes half an hour, I already have a read data store in my remote endpoint, okay? Data virtualization is one of my favorites because you just create a virtualized layer. You have your database, you create a virtualized layer, and you have your application reading that. I don't expect you to see that. But just saying because it's very easy for you to break your monolith wrong, right? And how do you use a virtualized database? You create a virtualized layer. Your monolith keeps reading and writing from the same. It's a virtualized database, but it's equal to the physical one. You want to extract a microservice. You create a virtualized database with just the data that you want to extract. You play a bit with your microservice. Everything is working fine. I think I split that correctly because everything is working. Then you can go and physically split your database to be truly independent, right? Virtualized database should be, I consider that to be a safety net. I didn't see any teams deploying virtualized solution just to deploy microservices, but I visited three different companies, and they said that they were very, very happy that they had a virtualized solution, because when they created their microservice architectures, they did it wrong multiple times. But when they did it wrong, they just had to delete the virtual database and start it over again. Nothing changed in the legacy systems. They didn't have any problems about that. They just need to change the new code, which is much easier for them, right? The event sourcing, which means, as I said before, the state of the data is a stream of events. So if you already model your system as a stream of events, it's very easy for you to. I've written a debit transaction here. I just need to propagate the same events through a message bus to get consumed to remote endpoints. Some people say that event sourcing is the perfect solution. I don't agree with that, because I did that myself, and I've seen many teams failing with event sourcing. People think that since you're using events, you have low coupling between your endpoints. But people don't realize that the coupling in your system are the events. So whenever you change the type or semantics of an event, you have to change your entire system to accommodate for these changes. So you have a coupling. These are the events. So I only suggest you to be using event sourcing if you have a very mature knowledge of your domain model. If you did that before, and you know that your events are not going to change, you're not going to add new events for this kind of architecture, and you have a greenfield model to be able to do that, right? You don't want to change your running code from snapshotting, a traditional snapshotting architecture, to event sourcing, because that's a lot of work, okay? But if you already have event sourcing, maybe it's perfect for distributing these events and consuming that in your CQRS endpoints. And the last one, change data capture, which is a set of tools that, which is my second favorite, this one. You just you have a legacy, you can't change the code, or you don't want to change the legacy code. How do you do that? You connect directly to the database. Or you have like multiple systems changing the same database. You can't change the source code of all of the other systems. What do you do? CDC tools connect directly to the database transaction log, and they start reading all of the insert, update, and alter table statements. They extract these events, and they propagate that to a message bus. So you have, some people call this poor man's event sourcing, but I think it's a very useful solution. You don't want to mess anything. You just want to create these events and consume and update your remote data stores. Okay? And a very nice open source project that implements a CDC tool is Debezium. You can go to this website, debezium.io. Currently, it supports MySQL, PostgreSQL, MongoDB. Oracle is almost final. And maybe somebody's working on a SQL Server driver, but I can't confirm that because it's open source. Somebody might be thinking something else. It's also sponsored by Red Hat. And I have a very quick demo here, which I hope to be able to show just a small part. Here I have a Zookeeper instance running. I have a Kafka bus running. Kafka is very useful for this scenario because Kafka is a bus that is persistent, and it's ordered on the same partition. So all of the clients will consume the messages on the same order. Oh, so you're not seeing that. So this is Zookeeper. Oh, Zookeeper, Kafka. I have a MySQL database running here. And I have a MySQL client, Debezium running. I have a Kafka watcher just for you to check which message you're passing through. And what do I want to do here is I'll just insert something into the database. I'll just update because just to give you a quick example. So use inventory. So I had IT 1004, her name was N Kresmar. I just changed that to N Marie, my update statement. Let's see what went through the Kafka bus. Debezium propagated this message on the Kafka bus, which is in a JSON format. If I try to format that for you to see, you can see that Debezium streamed a message in JSON format saying, well, my database schema was this before the statement, now it's this. It didn't change because that's just an update statement. But the nice thing about Debezium, if you get here, it shows you the payload before the update statement was N, and the payload after the statement was N Marie. So you can easily consume these messages on your remote endpoint and update your remote database with the changes that happened there. So you have some information here saying the operation was an update statement, and Debezium logs all the insert, update, delete, and alter table statements. So you can consume and update your remote endpoint. One question that people ask for me is that what happens if Debezium goes down? Debezium stores the point in the transaction log that it stopped on the Zookeeper. So if Debezium goes down, when you restart Debezium, it knows exactly where it stopped and start propagating the message since it stopped, right? So you never lose any message if you're using Debezium. And I'm already over time, but that's what I wanted to share with you. If you have any questions, I'm available later. And again, all of this content is available on my book, which you can get on developers.redhat.com. And thank you very much. Okay. We have some questions here. Let's see what we can create. Correct microservice when all business logic is DB procedures and functions. Well, that's a problem I didn't try to solve because I'm not a PL SQL expert, so I don't have a ready answer for that. When to not use event sourcing and what? Oh, before that, may I take a selfie because I need to show my family that I was really here. Okay. Hey. Oh, picture. Wrong button. Thank you. When to not use event sourcing or not? Well, I strongly advise you to, if you don't have an experienced person in your team that failed multiple times to do event sourcing, but how can you get expertise if you don't fail, right? So that's a good question. But I think it's very hard to do event sourcing properly. And if you want to do, I strongly, because one of the benefits of event sourcing is that you can have domain level events and propagate through your system. But domain level events are very hard to do it right. So what I suggest people, if you're doing event sourcing, you never did that before, start with low-level events. Which are low-level events? It's like customer created, customer deleted, customer changed. These are very low-level events. You can't change the semantics much later. You can't add the richness of the domain level semantics, but also you minimize the probability of having to change because these are very basic events. They rarely change later, okay? So you do a trade-off between power and breaking things. So in the beginning, I suggest you to start with the easy way, low-level events, and after you're an expert, you go to domain level events, okay? Store procedure trigger function is usually on the monolith database. Like in the customer, if you have PL SQL code in your customer functions, you're able to migrate that to your remote database too. But if you have like complex interchaining, you need to be able to split that. And if you have too much of that, I would say to you that customer is not a good candidate for splitting, right? You should get something that is more insulated. The other one, can we make only set unusually the column one before delete a column? Yes, you should never delete a column into production. You lose the data, you just mark that, you remove the not null constraints, you remove the referential integrity constraints, and you keep the column there until you know it's safe to delete. Like multiple. I'm saying if you deploy 10 versions per day, Like after 1 week, you're pretty sure that you deploy like 50 different versions to production and nobody's using that anymore. But if you deploy once a month, then maybe you have to wait 1 year. Okay? It really depends on your team. Is it possible to migrate CQRS architecture with zero downtime? Yes, of course. It depends on the integration strategy that you choose, right? So if you're using triggers or distributed transactions, not sure. But if you're using events, definitely, because you need to, then the compatibility layer goes to another level. You have to update the endpoint regarding your database, and you need to be able to have multiple versions of your events compatible between each other. So the same strategies that you apply to your database, you could be applying to the data model of your events, but then you have 2 different layers as a requirement to perform compatibility, right? What I suggest is that first you update your database in your endpoint, but you keep the same event format. And after you did that successfully, you change your events, right? Do you suggest to use something like ACL layer, access control layer? Well, I didn't dig through the access control policies here, but I'm just supposing you have authorization to perform any changes that you need. I don't know if that was the answer, the question, okay? In terms of Kubernetes, is it enough to build a strong consistency model for a microservice architecture with stateful sets and relational database? I think we're talking about different layers of abstraction. Because inside the relational database, you always have at least strong eventual consistency. Because true strong consistency, you only get with serializable transactions, which people rarely use. But at least a strong eventual consistency you get inside the database. What I'm saying to people is that you need to embrace strong eventual consistency in the application layer, right? And not only in the database. You need to be able to afford some eventual consistency on the application layer, because we as developers, we are used to think, wow, I have strong consistency always. But when you have a distributed systems, sometimes the data can get a delay to be propagated. And if you think about that, when you query your database, you transform that thing into HTML, and you show that to the user. When the user sees the information, it's already eventual consistent, right? Because somebody could have changed the database already. So we already have eventual consistency. The question is, how much latency between data updated and data changed notification you can afford in your business use case? And if you think that most of the critical business decisions are taken with click view reports that were generated on the previous night, you see that you don't need to be that strong consistent in your business application, right? Unless you're doing stock trading, which means you need the data right now, gets updated, I need to know. For the other use cases, you can afford like very high latencies of updates. If a procedure trigger function is used, what can we do? I think that's the same that we answered before, right? If it's inside the same bounded context, you can remove, but if you have like many things in between, maybe it's not a good candidate. Maybe you choose thing, and I would suggest you to remove, because you're doing integration down there in the data layer too. Okay. Was that all? Okay. Thank you very much.